everybody. In this video, we're going to talk about what may be the most famous concept from thermodynamics, entropy. Entropy can seem like a bit of an abstract concept, so we're going to try to spend this time demystifying what it is. Entropy is very closely related to the idea of equilibrium. Let's think about what this means in physics. Suppose we had a box of gas. Let's say we set up this box so that all of the particles of gas were up in one corner. What's going to happen if we now let the gas behave naturally? We would expect that the gas would expand and take up the whole box. This is just due to the way that gas particles behave. They're moving around more or less randomly and bouncing off each other, so they tend to spread out randomly in the box. It would be very, very strange for a box of gas with the particles all spread out to suddenly arrange itself such that all the particles were up in the corner. So there is a sense in which the natural state of the system is for all the particles of gas to be spread out in the box. Entropy is a way of quantifying this fact. Systems in nature will tend towards the highest entropy state. Entropy is often described as disorder, but this is a little bit misleading. It is true that there is a sense in which the box of gas with all the particles more spread out is more disorderly than the box of gas with all the particles shoved up into one corner. But it's not disorder in the sense of chaos. In fact, the maximum entropy state of this gas is the one that is the most uniform. It looks more or less the same no matter where in the box you look. There are two main definitions of entropy that we care about for this course. The first is the statistical definition of entropy, and the second is the thermodynamic definition of entropy. These two definitions of entropy turn out to be very closely linked, but it may not feel that way based on this introduction. Let's start with the statistical model of entropy. To do that, let's consider an example that is much simpler than a bunch of particles of gas in a box. It's the example we saw in DL today, the flipping of coins. Let's suppose we placed 10 coins on the table, all with their heads side up. Now let's imagine that we start picking up coins at random, flipping them, and then putting them back down. Given enough time, how many heads and how many tails do we expect to see on average? Well, it probably doesn't surprise you that we would expect to see approximately 5 heads and 5 tails. After all, if we're talking about a fair coin, it is equally likely to land on heads as it is on tails. You can think of this process as the system coming to equilibrium. We have some initial state of the system, 10 heads, which is equivalent to all of the gas in the particles being pushed up into one corner. We then allow the system to change in time. In the case of the coins, this change happens because we're flipping them. But in the case of the gas in the box, this change happens as the particles move around and bounce off of each other. As time passes, we move away from the highly ordered state, in other words, the 10 heads, or all of the gas up in one corner, towards a more quote-unquote disordered state. In other words, approximately 5 heads and 5 tails, or all of the gas in the box spread out. The nice thing about this example is that we can explicitly think about the number of states associated with these coins. For example, let's suppose we have 10 coins. How many possible configurations of those 10 coins can we have such that 5 of them are heads and 5 of them are tails? Well, don't worry if you don't know how to calculate this, but there turns out to be an explicit formula. You may have heard this described like this: 10 choose 5. In other words, we have 10 coins, and we're going to choose 5 of them to be heads. You can actually just plug this in to a search bar, and it'll give you a number. that number is the number of different configurations such that 5 of your coins are heads. And of course, if there's 10 coins, the other 5 must be tails. This number turns out to be 252. In other words, there are a lot of different ways we could end up with 5 heads. For example, our setup of coins could be heads, 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 tails, 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 or tails, 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 heads, 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 or tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, and so forth. There are a ton of different ways. In fact, exactly 252 of them. But how many ways are there for us to have all heads? Well, the answer is only one. It's just 10 heads in a row. There's no other option. We could write this as 10 choose 10. This is just equal to 1. Which one of these states has a higher entropy? Well, the statistical definition of entropy looks like this. Entropy is equal to the Boltzmann constant times the natural log of this value, omega. This value has a lot of different names, but for our purposes, we're going to think of it as the number of available microstates. But what is a microstate? Well, a microstate is just a specific configuration of the system we're interested in. With our coins, an example of a microstate would be a particular layout of the coins, say heads, 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 tails, 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 tails. That would be one microstate, whereas tails, 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 heads, 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 heads would be a second microstate. A grouping of these microstates that have something in common is called a state. For example, the state of our system could be 5 heads and 5 tails. There are a lot of different setups that correspond to this state, and in fact, we actually figured out the exact number. It's 252. So for the state where there are 5 heads and 5 tails, the entropy of the state is equal to the Boltzmann constant times the natural log of the number of microstates that correspond to that specific state. In this case, the number of microstates is 252, which would be plugged in here. But what about in this case, when all 10 of the coins are heads? Well, there's only one microstate associated with this state. It's just 10 heads right in a row. So instead of 252 going in here, we just have 1 going in here. The natural log of 1 is actually 0, while the natural log of 252 is fairly large by comparison. So this state here has a higher entropy than this state here. In other words, if we allow the system to change in time, we would expect that it would tend towards a state with 5 heads and 5 tails, and this matches with our intuition. It's actually possible to do this kind of counting with particles of gas in a box. We're not actually going to do this counting in this course, but let's just take a moment to think about it qualitatively. Let's go back to our example of gas in a box one more time. We said that if we push all this gas up into this corner and then let it go and allow it to move around freely, we would expect that the gas would expand to fill the box. The particles would sort of randomly distribute themselves throughout the box. In terms of entropy, why is this the case? Well, how many different ways are there for the particles to arrange themselves such that they're all up in one corner? I'm not actually sure about this. We could do the counting if we really wanted to, but we're not going to. What's more important is that we think about how that number compares to the number of ways that the particles can arrange themselves such that they're spread out sort of evenly around the box. Hopefully, it makes sense that there are much fewer options for the gas here than there are for the gas here. In the language of physics, that means that this setup has many more microstates than this setup, and therefore this setup has a much higher entropy. than this setup. Now, as I said, we're not actually going to calculate the number of microstates available for this kind of scenario. But there turns out to be a second definition of entropy that can allow us to shed some light on this case. The thermodynamic definition of entropy allows us to think about changes in entropy for systems that are exchanging heat. The thermodynamic definition of entropy looks something like this. But this may not be very enlightening. So let's rewrite this for a process that is happening at constant temperature, say a phase change. This just says that the change in entropy for this system is equal to the heat entering or leaving the system divided by the temperature of the system. What does this say happens to the entropy of a substance if we give it more energy in the form of heat? Well, it says that the change in entropy is positive because the heat is positive. But what happens when we're dealing with a process where temperature is changing? For example, if we're adding energy to a gas in order to warm it up. Well, we actually have another equation that can help us out here. C is just the heat capacity of the substance in question. Let's again consider what happens if we're adding energy to the system. If we're adding energy to the system, then we expect that the final temperature will be greater than the initial temperature. If that's the case, then the natural log of this fraction will be positive. In other words, the change in entropy will be positive, just as the change in entropy was positive here when heat was positive. On the flip side, if we're removing energy from the system, then the initial temperature is greater than the final temperature. And this natural log is negative, meaning the change in entropy is negative. Notice something else interesting about this equation here. T, temperature, is a state function, and entropy turns out to be a state function as well. Heat is a process function, but this equation actually allows us to relate heat to these two state functions. For example, if I gave you the temperature that a process was occurring at, as well as the change in entropy for that process, you could go ahead and calculate Q. Let's look at one more example to see some of the implications of this definition of entropy. Let's say we have two very large boxes of gas. One of these boxes is very warm, while one of them is very cold. What's going to happen if we bring these two boxes next to each other? Well, we would expect that the hot gas would start warming up the cold gas. The way you can think about this is that the hot gas will transfer heat to the cold gas. What are the changes in entropy for the boxes individually? For the moment, let's assume that these boxes of gas are so large that their temperatures are not changing. Because of this, we can just apply this equation here. Delta S is equal to Q divided by T. But what is Q for these two boxes? Well, we know that Q is the same for both. All of the energy that is leaving this box is going directly into this box. So the amount of heat for both boxes is the same. This one is losing energy, and so the heat is negative, while this one is gaining energy, and so the heat is positive. But what about the entropies? Well, Q is the same for both of these boxes, but T is not the same. This box here is very warm, and so its change in entropy will be less than the change in entropy for the cold box. But what does this mean about the change in entropy for the whole system together? Well, because this box is losing energy, because heat is negative, its change in entropy will be negative. While this box over here is gaining energy, heat is positive, and so the change in entropy will be positive. But because the change in entropy for this box is larger than the change in entropy for this box, the overall change in entropy for the entire system will be positive. This turns out to be true universally. We call it the second law of thermodynamics. We write it like this. For any closed system, the change in entropy is always going to be greater than or or equal to 0. Now note, this does not mean that for any system you can imagine that the change in entropy will always be greater than or equal to 0. A good example of something that violates this is the human body. We, as humans, are able to maintain our bodies in a low entropy state. But in order to do this, we constantly have to be consuming fuel and excreting waste. One way to think about what we're doing is that we're increasing the entropy of the things we consume in order to keep the entropy of our bodies low. But this is okay because our bodies are not a closed system. There's constantly stuff coming in and out. However, if you do have a truly closed system, then the second law of thermodynamics will always apply. As we said before, entropy is often described as disorder, and the second law of thermodynamics is sort of described as a rule that says the amount of disorder must always increase. This is kind of true, but disorder doesn't really tell the whole story. And hopefully this video gave you a clearer picture of what entropy really is. Next DL, we're going to introduce one last thermodynamic idea. It's the idea of Gibbs free energy.